Yeah, and here's I have opened up a the IBM Open Science Challenge. For those of you that don't know about this, definitely check it out. Sign up for it. I encourage everyone. Um, so I'm going to read a little bit of it and go over it from like my understanding. That way, you guys can learn a little bit. And this is basically a part of my study guide. I normally do a study group Wednesdays and Fridays. Since people haven't been really showing up, I'm just going to record some of them and um, post them on YouTube, maybe on Vimeo, other things like decentralized things so they don't just get censored from one corporation to another or whatever, because, I'm not into censorship. Anyway, so this challenge is about finding the triple X Hamiltonians of a Heisenberg spin model. Now, excuse me, what that means? There's plenty of things, honestly. Make sure you read all this. Now, if you haven't already, get a copy of it. I am going to open my GitHub real quick, and we shall. So I have a copy of it in my personal GitHub as well as the open source repository that I have made. It's a quantum code matrix. You're also free to try and join the quantum code matrix. Basically, it's just it's a way for everyone to kind of learn more about quantum computing and other things like that. Let's see, I'm just logging in now. If you haven't already, definitely get a IBM account, sign up, it's free. They give pretty much free, you can run all your, you can pretty much run most basic programs and codes with your for free. If you use it like intensely, I think that's when they start limiting you, but it's more like if you're using it as a business. I still haven't even reached that, and I've been using it, maybe like once or twice a week, actually running things on a real quantum computer. It's pretty cool. If you haven't learned about quantum computers just yet, definitely learn more, check them out. They are the future. We might be living in a quantum computer right now. We might be in just one bubble universe after another, just riding the waves of reality. Who knows? Definitely gonna try and find out, eh? Let's see. Okay, signed in. I'm just gonna pull up. So, feel free to take a look at the quantum code matrix. I might share it in the description, but here is the repository I'm talking about, right here. https://github/quantum-code-matrix/open science prize 2021. So this runs until April, so it's pretty awesome. If you want to join my team, definitely hit me up, let me know, and we can try and get it together. I think I have 2 more open slots. That's if the 2 other members don't fall out because I've been basically just doing it by myself anyway. So, Open Science Prize, you know, it's closes in April. You can register there April 16th, 2022. So yeah, pretty cool. The main things you want to keep in note is basically how you're going to be judged. So performance is measured by the state tomographic fidelity in comparison to other submissions. Maximum of 15 points. So that's probably the most important is performance. And then clarity of documentation provided in solution code. I've always had a problem with documentation clarity, so that might be a weak point for me. Creativity and a unique, innovative, original solution. So that's 5 points as well. So yeah, it's pretty cool. I'll share some of the code I've played with, and I know, right? How can I share my answer before it's even... I'm just kidding, my answer isn't the answer anyway. Not yet. It's an answer on trying to find the answer, so. Right. I'll read the introduction, maybe a little bit further for you, and then we will look at some of the code I've tried. So if you actually run the code on a real quantum computer, you're going to get different results on different days. Surprise, surprise. Reality changes every time you measure it. Whoa. That's pretty deep knowledge there for you. Okay. So let's take a look. Introduction to Quantum Simulation 1-1. Anyway. One of the leading uses for quantum computers will be to simulate quantum systems, such as molecules or engineered materials. Actually executing a quantum simulation on a current quantum computer, however, can be difficult and error-prone. Your objective for this Open Science Prize is to significantly improve the state-of-the-art for quantum simulation. Details in Section 2. The quantum system you will simulate is a quantum spin 1.5 model, where each qubit represents a quantum spin 1.5 particle in a 1D chain. Quantum spin models have some amazing properties and uses. Computationally speaking, certain optimization problems can be mapped to spin models and hence minimized on a quantum computer. Physically speaking, spin models show a variety of quantum behavior, such as large entangled states, quantum phases of matter, quantum many-bodied effects, and many other open questions in physics research. There are many different spin models, but we will focus on the XXX Heisenberg model. We're not talking about no naughty num-nums here. Though it is not as well known as the transverse field Ising model, the XXX Heisenberg model is of practical and theoretical interest. It may also be difficult to simulate, which is where we come in. Alright. The notebook is organized as follows. Section 1, labeled 1x, provides you with brief instructions to the XXX Heisenberg model, time evolving a Hamiltonian and decomposing a time evolution operator into gates for a quantum computer to execute. Section 2, labeled 2-x, outlines the specific requirements and boundaries associated with completing and competing in the Open Science Prize. Continuing from Section 1, the notebook shows an example solution. So, now that we've introduced it, let's run everything. Basically just, shift enter all the way to the bottom, because, yeah, you need to much need to write on everything. So it comes with a predefined solution. It's not very good. It's like maybe 15% fidelity or less. I can't remember. The current answer I've given it is even worse than that. So my answer, or this answer, that like, don't copy it. Like, it's pretty much waste. It's just me trying ideas and seeing what works and what doesn't. So that's how I kind of live my life, you know, trial and error. All right. So there's a bunch of code, right? They import NumPy and the matplotlib. This is basically so that you can manipulate numbers and work in graphs and things like that. Good stuff. Here they define some function. Let's see, returns matrix representation of XXX Heisenberg model for a 3-spin 1/2 particles in a line. Cool. And they call that function. This is what it spits out. So I think some of the, like, if you're studying this with me, they do ask for like the certification to get what is that called? So basically be able to sometimes like see the answers and put them into graphs or charts, things like that. So definitely try and learn that. Moving along now. See, this is where they basically take that and graph it for you so you can visualize a little bit of it. Find an array of time points, initial state. Okay. Plots the evolution, and then you can see time of the Hamiltonian as it, so this is 1 second, 2 second, 3 second, and then the probability of the state. Tell. So as it begins, it's further away than the state they want. And then as it evolves later on, it's further away from the state they want. And I think you probably want this state right here, the lowest energy state. At least it's normally how these things work. Right. Open Science Prize, judging criteria, terms and conditions, registering the website. Yes, we've covered that. Okay. Alright, so let me see. I think I am running on a quantum computer, so it may take a long time to finish. Looks like 2 of our jobs have been submitted successfully and run successfully, so yeah, it might be taking a sec just because I'm running on the actual quantum computer. I'm not running on just the simulator. So definitely use the simulator when you're just trying to trial and error things, because quantum computer, getting access to the quantum computer right now, you're basically fighting for access to it with other people running on the Jakarta, because that's the only quantum computer they want to run things on. I'm sure it's because, you know, they've put in some security measures or something, or they just want it specifically on Jakarta so that they can measure it easily. Who knows? So this is the code that I've been manipulating. If you notice, it is different from the code, from the original code. I will produce that in just a sec so you can see the difference. So some of this code basically would be like copyrights for my own knowledge, I guess, because I've edited this. This is all me. This isn't anyone else. If you copy it, I mean, you won't get anything out of it, but it's still owned by Jeremy Ritter, so it's just that. Until, you know, I release it or whatever. Since it's open science, it's gonna be probably released anyway, but their solution is actually better performing than the one I have there, so this is pretty much useless code, except for, you know, if you're actually trying to gain experience and learn how to do things, then it's not useless code, then it's gold. Gold, I say. Anyway, I think I found it. Let's see. Tis gold, I say, gold. Are we all ready? Right, so let's compare the two. Okay, so this is mine. Please down below. It's almost done running the job, and then it'll measure how well the code works with the solution they are trying to achieve. So if you don't know a lot about the Hamiltonians or the XXX model, definitely check out Wikipedia. Plenty of resources in the internet. If you live in a country that is trying to, you know, like censor information, try and look for decentralized internet applications, and then use Tor, anything you can, you know, to find the information, because I think information should be free for everyone, and no one should block out information for people. We should all own it. And yeah, I mean, it's almost done here. But let's go back. I'll tell you what my code is doing, and then I will pull up their original code and tell you what it's doing. So, here, this is just the basic stuff. This is all their code, pretty much. IBM's code, until we get to, I think about here. That's where I started editing. Just read the notes, you know, the final time of the state evolution, number of trotter steps, because they want at least 4 trotter steps, so you can add more. I've noticed that if I add more, it actually gets less accurate. I've also tried, I've also been trying to get it to where some of these are in between the trotter steps, but I don't know how to do that just yet. And there's not really too much logic behind what I'm doing here, but I'll explain what it's doing. Alright, so QCH on 0, that's basically this. It is putting qubit 0 into superposition for you. Boom. And then RZ, RY, the first digit is the qubit, and then what, oh sorry, what the first digit is. Sorry, I'm doing this off memory. But the second is the actual qubit. So see where it's on position 2 or on qubit number 2, which is actually qubit 3, but you know, since the things are red 0, 1, 2, it's the third, even though it's, yeah. Computers are whack, yo. So these are what these two gates, or what these two do, are basically just spin the qubit a certain direction. So bada bing, bada boom, little qubit magic there. Don't modify this code, okay? And then I went further. Then I tried MTC, which is this trolley gate, and it's like basically a giant CNOT gate, and it entangles these three together, and then it changes this one based on these three. Cool, cool. Okay. And I put an H gate here. This barrier does not need to be there. I'm sure it's not even doing anything. It was just like, maybe if I make it harder for a qubit to affect other qubits, it might have something to do, but it really doesn't. It hasn't affected the system much, if at all. So that's it, and then visualizing it, this is how you do it. So QC step -1.draw, and then it shows you everything. So that's it. These are X gates, which flip the regular qubit from 0 to a 1. And then this is measuring the results. So, how did we do? We got 0.1101 plus or minus 0.0027. That is not very good fidelity. That is terrible fidelity. We are shooting for, I believe, 30 to 40% fidelity, so pretty far off that, huh? That's why I said, like, the code I am exhibiting is pretty much not going to help you. You can try it, play around with it. It's not going to help you. Now, I'm going to go ahead and comment all this out, and then I will add the original code for you so you can see the difference. And IBM's code, like, is a little better in fidelity wise. Why would you want worse fidelity? So you know what a wrong answer is, you know? Like, what was that saying, that one dude, Thomas Edison or something, who tried like 1,000 different ways to light a light bulb before he found the actual one that does it? Terrible way to learn. But it works. Okay, here we go. Now I will paste this and run again. So this is different, see? Just 2 X gates, bunch of trotters, and then we'll run again, and run again, and run that again. How about that? So, this might take a sec. It looks like it's running faster than the first one, so it doesn't look like there's many people running any jobs on Jakarta, which is nice. Once I waited like 3 hours, so we are running on an actual quantum computer, so that's it's an amazing feat for humanity. Good job, humans. Good job, us. Way to go. We're on the next steps to becoming magic wielders, whatever. You know, they say technology super advanced would be indistinguishable from magic, so you should totally believe in it. I'm gonna change this title. That's hilarious. Your browser can't play this. Liars. Of course it can. Let's go. Is it? Oh, it might take a sec. Let's see. Number 2 queued. Enjoy the music while we wait. We'll turn up the volume on the music for if I have to restart the entire kernel. Okay. Now run. So now we compare the fidelity. This is on the simulator, since the quantum computer is kind of that's hilarious. So apparently my code was running with higher accuracy than their basic code. That's surprise. Well, there you have it. So mine is like 11. So this is like 4% accurate. Not very accurate. Mine is like 11% accurate. So it's a lot higher fidelity than 4%. That's a bit surprising, but you know, since it's still quantum computing, the answer changes day to day, so who knows why. I'll definitely find out in the future. Keep programming and seeking out answers, shall we? So, let's go over what we learned. We learned about the IBM Open Science project. That even my trash code is running better than the basic answer that they gave us in the beginning. Still pretty surprised about that. When you're doing this, definitely open up the Qiskit documentation. I'll show you this. This is going to help you a lot. Qiskit. So have this open, and then go to their documentation. If you haven't already, read a bunch of the documentation. I know it's boring, but it's pretty much what'll help you a lot with this. You can do optimization. There might be some things in finance that might actually help there, and then nature is mostly where you want to spend time, just because we're working with like basically chemistry simulations. So go through this. You'll want to focus on like ground state, excited states. Those two probably. And then there's another thing when you're reading the supplemental stuff. Right? This is getting down to like hardcore quantum computing, where you're basically telling the quantum computer the exact pulse you want the qubit to take next. And they talk a lot of it, or it shows a lot of this. So go through this. It talks about the Heisenberg model, goes through some more math for you. I'm not going to read over this just because all this the way I did it. like Google Scholar or other search engines. Those should help you. Something like that. So academic, maybe try a bunch of them. Google Scholar is pretty good. Research, Microsoft Office is decent. There's a whole bunch on their web. So this is a list of 20. So yeah, Base, Zeotech. Try any of these. Science.gov, Semantic Scholar. So go through all those. Try this if you like. Heisenberg. Complex model. Look up some of these. And it should give you a PDF, right? You'll want to open that up, read through it. This is just, you know, there's a lot of reading in when you're a scientist. I know it's boring, but if you get through it and you actually, like, don't believe everything you read. Like, never believe everything you read, because our brains are designed a certain way, and you can pretty much hack your brain to believing anything. So don't believe everything you read. Definitely question everything. This is good information still, you know. Not to say that, like, the scientists don't have it right or something. It's just like, it's more about, see this is bullcrap right here. You should not have to pay any money for information. I don't care who you are, or, like, that is disgusting. That is just bullcrap. Anyway, read as many free papers as you can. If you can't get them for free, try and find another way to get them for free. There's a bunch of ways to get things for free that, yeah, so, I hope you enjoyed this. Hope you found it meaningful in your life. It might have been a little bit dry, but I tried my best, and I hope you enjoy sitting with me. Here's to the next couple of transitions in our lives. You know, we're gonna get it's gonna get pretty cray-cray in the multiverse.